Hi Science2 kiddos. I'm going to use these slides to review the Hewitt chapter 5.1 through 5.4 readings, all about gravity. So everything goes back to the legend of the falling apple. I don't know if this is true or not, but Newton observed that an apple falls from a tree straight down, and if that happens, then why doesn't the moon do the same thing? Because gravity is affecting all things in exactly the same way. And the answer to that, why doesn't the moon fall back down to Earth, is due to what's called tangential velocity. In other words, the moon is moving incredibly fast parallel to Earth's surface. But at the same time, there's gravitational attraction drawing the moon towards the center of the Earth, and so that sort of holds it in place. And so rather than, you kind of have to rethink your understanding of orbit as the fact that the moon is actually just falling around the Earth. So it is falling down just like an apple would, but it's also moving sideways so fast that it's never actually going to strike or hit the Earth. You could do the same thing theoretically with an apple, right? We could launch an apple into orbit. You just have to throw it sideways with enough speed that it would never actually hit the ground. It would have to match the curvature of the Earth. We'll talk more about that later, and that's exactly what we do with satellites. If Earth were to suddenly disappear and that gravitational force holding the moon in place gone, then the moon would shoot off in whatever direction where the moment that happened, because then the tangential velocity would take over. So Newton made huge discoveries relating to gravity, and this led to Newton's law, which I know is a confusing looking equation right here, but basically think of F as the force of gravity measured in newtons. And it's basically showing that gravitational force, when two objects, they're directly proportional to the product of their masses. That's why you have mass 1 and mass 2 on top here. And then they're infinitely proportional to the square of the distance. That's why you've got distance squared on the bottom. And that is just a fancy mathematical way of saying that the bigger an object is, the more gravitational force it's going to exert. I have a water bottle next to me. Technically, there is gravitational force between me and that water bottle, but I'm not going to attract that water bottle to me anytime soon. However, when you think of the entire planet Earth at my feet compared to me, if I were to jump up, I would fall right back down again, because Earth's gravity is so strong. There's so much mass there that it's pulling me towards itself. But the farther apart objects are, the weaker the gravitational force is. So again, we are on Earth's surface. We're very close to Earth. We're attracted to the Earth. The sun is not going to fall onto Earth anytime soon because it's incredibly far away, and vice versa. We're not feeling all of the gravitational force of the sun, which it exerts a lot because it's so far away. Now, can we quantify how weak gravity gets based on distance? And you can. It's called the inverse square law. And again, I know this sounds a little confusing, but I'll do my best to explain this simply. But again, along this trend, the farther apart objects are, the weaker the gravity is. And it turns out for every kind of unit of distance, the gravity goes down or decreases by the inverse square of the distance between those two objects. So think of this as, let's say we have an object here that is a distance of 1 from our center of gravity. So there's your gravity right there. Well, if we have another object that is exactly twice as far away, right? So that was the original distance. Now we've got it twice as far. Notice that it is now 1/4 the strength of the gravity that it is experiencing. And if it was 3 times as far away, well, then it's 1/9. And again, you can see that that's just 1 over the distance, the radius squared, right? 2 squared is 4, and 3 squared is 9. We can demonstrate this with a little activity. You can take $2 bills, or just 2 bills of any money that are the same size. And if you hold the unfolded one close to your face, and then take the other one and fold it twice so that it's 1/4, and hold it twice as far away. You hold the unfolded bill twice as far away. Hold the folded bill closer, and you can actually get them from your perspective, if you're looking with one eye, to look exactly the same size. You can do the same thing with your hand, where if you hold your hand in front of your face and hold your other hand twice as far away, when you look with just one eye, the hand that's farther away will look like it's about 1/4 of the size. And that's just a demonstration of the inverse square law. Think of gravity as reducing that way with distance. Hope that was helpful. Thanks.